In this video, we're going to talk about finding the maxima and minima on graphs. So I'm looking at this graph, and I only want to look at the interval from -4 to 5. So instead of looking at the whole graph, I'm going to stop it. So 1, 2, 3, here's -4. So I'm looking from this point of the graph up until 5, which is right here. So to this point of the graph. And when I look at just this piece of the graph, I want to know, are there any maximums or minimums? Now, there are a couple of different ways that we're going to define these, and we're going to look at these more specifically. But a maximum is the highest point. So I have a max right here. And a minimum would be the lowest point. So I definitely have a minimum right here. Now, if I only focused in on maybe just this little section of the graph, I'd say, well, there's a maximum here, and there's a minimum right here. So we have a difference between what we call absolute max and mins and relative or local max and mins. And that's what we want to look at. So our extreme value theorem tells me that if I have a function that is continuous, such as that last one, on a given interval from a to b, a closed interval, there has to be an absolute minimum and an absolute maximum on that interval. If it's continuous, that's going to happen. So if I just have any graph, and I look at a set point, there's an absolute min and an absolute max. Well, the absolute max, if I'm only looking at that interval, could be right here, and my min would be right here. So it's just saying there's always a max and a min on any continuous function. The local extreme point theorem says that f has a local maximum or a local minimum, so not necessarily of the whole graph, but of a certain area, that at that value of c, if our derivative exists, then the derivative has to equal 0, which kind of makes sense if I'm looking at a graph and I focus in just on this little region right here, and I say, oh, right here there's a local min. Well, the slope at that line, it makes sense that the slope there would be 0, so at some point my derivative has to be equal to 0. So we talked about an absolute max and min, a relative or local max or min. We also have what we call critical values. And critical values kind of encompass a lot more. So a critical value is for any value of a in the domain, either the derivative equals 0 or it's undefined. And a lot of times we forget that one. So it's either equal to 0 or it's undefined. So if I'm looking at this graph, I have, it looks like a local min right here. Right here, even though the graph is continuous, it's not really because it's making that cusp. That would be undefined. So this says I would have two different values that would be critical values, when x is -2 and when x is just a little bit less, so at about -0.4. So knowing this information, we can use our derivatives to help us find extrema. So it says find the extrema for f of x equals x cubed minus 6x squared plus 9x plus 15 on the interval from -5 to 7. Now this is a polynomial function, so I know it's continuous. Well, in order to find those extrema, it's either going to be where it's 0 or where it's undefined. So I need to find the derivative to find out where it's 0 or where it's undefined. Now because this is a polynomial function, the derivative will never be undefined, so I only need to know where it equals 0. So my derivative is 3x squared using power rule minus 12x plus 9. So I want to know, when does that derivative equal 0? So I'm going to set it equal to 0. So 0 equals 3x squared minus 12x plus 9. I can factor out a 3. So I'm left with x squared minus 4x plus 3. And this factors to 3 times x minus 3 times x minus 1. So I know at x equals 3 and x equals 1, I have a local extrema. So now to figure out which would be a max or a min, I can actually evaluate them. So if I want to know for sure which is a max, which is a min, I'm going to evaluate them. So I'm going to say find out what's f of 3. I need to find out what's f of 1. And now if I want all my extrema, I also have to look at the endpoints. So I also need to find f of -5, and I need to find f of 7. Okay, so when we do our calculations, f of 3, I plug 3 in, so I have 3 cubed minus 6 times 3 squared plus 9 times 3 plus 15. I do my work. It turns out that f of 3 equals 15. When I plug in f of 1, I have 1 cubed minus 6 times 1 squared plus 9 times 1 plus 15. I get 19. When I plug in negative 5 cubed minus 6 times negative 5 squared plus 9 times negative 5 plus 15, I get negative 305. And then when I plug in my 7 cubed minus 6 times 7 squared plus 9 times 7 plus 15, I end up with 27. So when I'm looking at this, I can see that I have an absolute minimum at negative 5. I have an absolute max at the 27 because those are the endpoints on my interval, but I also have local max and mins at 3 and at 1. So when x is 3, there's a local min. When f is 1, there's a local or a relative max. So because I'm looking at the endpoints, I have to include those. The derivative I found, it's equal to 0 at 2 spots, so they have to be maxes or mins. When I plug them in, I can see 15 is definitely lower than 19, which is why I know that at f of 3, it's a local min. Okay, we want to find the absolute max min for f of x equals x to the 4th minus 2x to the 3rd on the interval from negative 2 to 2. Well, let's just find all the max and min. The work really isn't that much different. So I need to know when the derivative would be equal to 0. So I'm going to first find my derivative. So I'd have 4x to the 3rd minus 6x squared. I want to know when that's equal to 0. So I want when 0 equals 4x to the 3rd minus 6x squared. I can factor out a 2x squared. So I'm left with 2x minus 3. So I get when x is 0, or when x equals 3 halves, I could have a local max or a min, but I also have to include my endpoints. So to verify where that max is, the absolute max, the absolute min, the local max, the local min, I have to evaluate all of them. So I have to calculate f of 0. I need to calculate f of 3 halves. I need to calculate f of negative 2. And I need to calculate f of 2. Okay, so we plug in 0, we get 0. If I plug in 3 halves, I do some work, I end up with negative 27 over 16. If I plug in my negative 2, I end up with positive 32. And when I plug in positive 2, I end up with 0. So here I can see my absolute max is the 32. Okay, that's the absolute highest output I have. 32 is my highest number. At 3 halves, I get my absolute min. And then at f of 0 equals 0, I also have a relative something, but we're not quite sure what it is without more information. Okay, so in this one, I just gave you a picture of the graph so we can kind of see things. So remember, critical numbers are points on the graph where either the derivative is equal to 0 or it's undefined. Well, as I'm looking at this, right here at x equals negative 1, that would be 0. At 3/6, it's going to kind of change direction right at that spot. Right here it's going to be 0, right here it's going to be undefined, and right here it's going to be 0. So we have all of those are our critical numbers at x values of negative 1, 3, 5, 9, and 11. Those are our critical values. Those are the x values that are critical. Now our relative maximum is any points that are relatively higher within this graph than anything else. So I have a relative max at the point 515. And then I have a relative minimum at the 11, negative 8. Because relative to the rest of the graph, those are low. Now my endpoint outputs, I have endpoints at 3, negative 10 and 13, 1. So my endpoints are negative 3, negative 10, which would also be a minimum. And then we also had an output of 13, 1 was our other endpoint. So now when I want my absolute maximum, it says look at all the y values and which one is the highest. Well, that one's the 515. My absolute minimum is the lowest y value, which is that endpoint 3, negative 10. Now the other ones that we haven't quite talked about yet are what we call inflection points, and we're going to get more into those into our next unit. But our inflection points are those 3 other values that we haven't talked about.